The last section of this chapter sets up two applications to everything we've been talking about. Now, the first application, there's not going to be many calculations you can do with it, but it is an interesting phenomena that has many applications, so I'll try to talk a little bit about it, but these really aren't going to be the most common things that you deal with from this chapter. So the first thing we'll think about is called an interferometer. And the idea of an interferometer is that we're splitting a single beam and we're recombining the beam later. So because we have one initial beam, that means we don't have to think about a phase difference, an initial phase difference between our two beams. We again simplify to the scenario where we have identical sources and we only have to think about path length difference to think about the interference. We will then be looking at the differences between the two paths. Again, this is just path length difference, what we've been talking about the entire time. And we're going to be doing a few potentially different things with this. One is to just look at the difference in path length. And again, there'll be some reasons you would want to do that, normally looking at the change in one of the path lengths. However, a different option is to actually pass one of the beams through a material and to learn about how that beam interacts with the material. So an obvious situation here would be to measure the index of refraction. If one beam passes through air and the other passes through a material, you can actually use this to get the index of refraction of that. When we talk about measurements in this case, this is always going to be looking at the interference pattern, which I'll show you in a little bit. So we're going to be normally looking at changes, and in our interference pattern, we're going to be asking, are we at a position that has constructive or destructive interference? Now, what you know at this point is constructive interference means that you have a path length difference of an integer number of wavelengths, but you don't just know if that's 2 or 3 or 32 wavelengths. So we make small changes to see how many times we go from constructive to destructive. So there's kind of a subtlety in how we actually make the measurement here. And I'm not going to go into great detail since this won't be the most important application from this chapter. So one specific interferometer we'll look at is the Michelson interferometer. There are multiple types of interferometers. The Michelson one is kind of the most common. We have a couple of them in the lab, and understanding this will then allow you to understand different ones as well, other geometric configurations. So we have a beam splitter, which is basically a mirror that lets some of the light through and reflects some of it. And then we have two other mirrors. So how you can think about this is that we have a beam that comes in and it hits the beam splitter. It then one of them bounces off, up to the mirror, and comes back down. We can then think about it passing through the beam splitter and coming to your eye. Now, another one is actually just that initial path that then passes through the beam splitter, bounces off this mirror, comes back, and now bounces off. So in each of these cases, you have one transmission and one's reflection. Now, if you say, hey, what's to stop this from passing through? Well, it absolutely can. And similarly, this light here could actually bounce off and come back, but notice that that's just going to keep going. Nothing happens then. So there are some paths here that we're not talking about, but in particular, there are two options we are interested in. One where it bounces first and then transmits, another where it transmits and then bounces. So in this case, you have two beams now that are coming back to your detector. The physics technique is to show an eyeball here, but we would usually be using a real detector and not just an eye, or, that's still like in your head. So one of these mirrors is usually fixed in place, and then the other is movable. And what we're looking at here is the interference pattern that we get. Now, this is going to be our circular interference pattern where we have a really bright spot, and then we have a dark spot, and then we have a bright spot again, and so on. You see circles. And what we're always doing is looking at the very center. So we move this mirror a little bit, so there's an adjustment screw, and you can make just a really small change, and we'll see the center here get dark. And so we've gone from having constructive interference to destructive interference, which means you've actually made a very small motion here that we can express in terms of the original wavelength. So one thing to note is that we have some distance here, L2, but it actually bounces on this twice. So if we actually move this a little bit delta x, our path length difference now would be twice delta x. So when we say not necessarily the path length difference between the two beams, but just as we turn this, how does the length that one of the beams goes? Well, that's actually equal to 2 delta x. So this derivation can have some factors of 2 pop up that are not entirely obvious. So what are the applications of this? Again, I'm not going to go into the specific equations for the Michelson interferometer, since you need to be able to think through what's going on with the different paths so that if you're shown a different interferometer, you can understand that one. But there's some really neat applications. So first, you've possibly heard of this before. If you haven't, it's something you can study in modern physics, is the Michelson-Morley experiment, which was actually looking for the ether. So we've been talking about light and waves for a couple of weeks now, and we've said that light doesn't travel through a medium. Every other type of wave travels through a medium, but light doesn't. This was actually something that people had a really hard time understanding about 100 years ago. People assumed that there must be some medium all around us that light traveled through, and they called it the ether. And there is an experiment to basically look for the motion of the Earth through this ether. And not going to go into the details now, but it was done with the Michelson interferometer, and the answer was nope, the ether doesn't seem to be there. And nowadays, that's the only context we talk about the ether is. We talk about the experiment that showed it's not there, and we understand how that can be true for light. We have this different model of how light works. Now, a second application that you've possibly heard about is the LIGO experiment, which actually uses an interferometer to look at gravity waves. Now, this is really neat, and that basically they set up an L-shaped interferometer, so there's two really long arms that are on the scale of kilometers. These are incredibly, incredibly long. And they are again looking at the interference when the two beams come back together. But what they're doing is actually looking for a distortion in space itself due to a gravitational wave passing through. And depending on the direction that the gravitational wave passes through, it stretches or contracts one side of the L, but not the other. And they've actually detected gravitational waves this way. So this is like gravity is distorting the space between the initial beam and the final mirror that it hits. So this gravitational wave announcement was made very, very recently, and they're just an awesome, awesome experiment. So then there's a couple other things we can do. So one is we can measure the difference of the index of refraction of air from 1. Now, if you only are interested in 1, 2, or 3 sig figs, we would say that the index of refraction of air is 1, but it isn't equivalent to vacuum exactly. So there's an experiment that we do in modern where you can in advanced lab. We have an experiment here, I don't remember which class I use it in, that you can actually use this technique to measure the index of refraction of air. Now lastly, you can also do this with just measuring small distances. That if you're trying to measure a small distance, just moving the mirror a little bit based on that small distance will change this interference pattern quite a bit. So there are kind of 3 very specific applications, but it's something that can be very widely used as well.